Okay. Good morning. So last time we distributed a midterm exam. I only got a few students did not pick up. If you happen did not pick up the exam, we better, after class you go to my office, then we can distribute the exam instead of distributing here. Okay. If you have some problem on, understanding the grading, like which question, get points off, what should be the right one. I've been asking TA to write something on the major points of the grading. The TA did not put, of course, ideally you should put some why, what are the points you're missing, you got some points off. The TA probably with so many, exam sheets to grade, he or she just put some points, did not say why the points were taken off. Which, of course, you can discuss with TA during the office hours. But I have been asking TA to work out some major points and post somewhere, so you can look at it to check why. If you feel the grading is not quite fair or something, you can discuss with TA or discuss with me. We can reevaluate some questions. Okay. So that's about the midterm exam. So this is the first one. Then we'll have the second one almost at the end of April. So the second one, based on our original, promise, the technical contents covered by the first part will not be covered by the second exam. Simply says you already mastered that part is a good one, but in the meantime, we separate the exam. It's two midterm, it's not a final. So it will not take care of the first midterm, that part of technical contents. Okay. Do you have any questions regarding this? Okay. Yeah, so overall, our exam score is pretty high. Still, like average is around 90. Okay. But if you still, find something, the grading may not be quite fair, feel free, we can discuss. We will continue our discussion on the class type. Okay. Last time we just give you a little briefing. Okay, briefing means a little quickly to go over the previous one. See where's last time we said from the massive natural language text, okay, we first perform some phrase mining. We get necessary phrases like San Francisco could be one phrase rather than two, right? And then you go over, try to get the types out by doing distant supervision. So-called distant supervision is you may have Freebase, Wikipedia, DBpedia, Yago, those kind of, they already give you the type. You want to use this type doing the propagation down to the text that you are analyzing, the corpus. And we also mentioned that there are lots of challenges. For example, you may have name ambiguity. You may have context sparsity. Then we try to, do it step by step, try to solve this problem. Okay. And essentially, the solution, there are mainly three parts. One part is we try to use minimal linguistic assumption. So-called minimal linguistic assumption means we may not use strict parsing, or especially semantic parsing may need a lot of people to do tagging and curation. That may not be realistic for very dynamic, very large corpus. And that we only do something like a part speech tagging. Okay. And using this, using phrase mining, we may be able to grab the key components. Okay. Then what we are going to do is doing like, using this different mentions, try to build with distance training, try to build bridges. And then another important thing is based on relation phrase, we can cluster them. The bridge become wider and broader. Okay. So let's look at a little more detail. Okay. That means once you do the part of speech constraint phraser segmentation, that means you do phrase mining, you find the phrase, you go back to the contents, okay, to the text. You try to do phrase segmentation. That means you may say, support vector machine is a phrase. You get this. But in the meantime, you want to use part of speech constraint. That means you try to say this part is likely is a noun phrase, this is a verb phrase. You base on the part of speech, you will be able to get something better. Okay. For example, the thing like food was good is not a phrase. So you, by part of speech tagging, you will drop this one as a phrase. Okay. Then with this, you try to construct the graphs. We call this one just different parts. It's generally is a heterogeneous graph. So-called heterogeneous, you have different things. This part, like C, is the surface name. The round one is a relation phrase, like this has office at, is ally, those relation phrases. The ellipse part essentially is an entity mention. Okay. You want to, based on this entity mention, linking to the surface name and linking to those relation phrases, construct this heterogeneous graph. Why we want to construct this heterogeneous graph? The reason is something you can find based on distance training, like from wiki, from Freebase, you can find it. You can get a type, or at least a candidate type. Okay. With this candidate type in a very large corpus, you are going to use these links to try to propagate. How to propagate? Of course, one way is they link each other. They may link to like these different Washington surface name. They may link to Washington. The other one may link to Kabul. Okay. But another important thing is you probably see these relationships may help each other. Okay. That means if you do relation phrase clustering, you may help each other. Just give you a simple example. If you look at this P3 and P4, if you do not know Washington, whether it's a location or it's an organization, but suppose you got this one says something like this one is Kabul or some other, it could be like, another government, like a Canadian government, may say declare something. Okay. Then you probably can see this government or this organization declare something. And now you see Washington announces something, okay? But declare and announces their left-hand side. Who declares, who announces likely is an organization rather than a location, okay? So then this cluster will help you to say likely Washington will be at this point, will be an organization rather than a location, right? Because the organization can announce something. The location will not be able to announce something. Okay, you probably can see, because announce, declares, all these things are synonyms. Okay, you find in the cluster, it will help you to propagate one type to the other type. Okay. Remember, all these are soft in the sense it is a distribution. Finally, which distribution dominates, which one is a winner. Okay. So you probably can see the whole graph, how it flows. It means we may have type propagation on the heterogeneous graph. That means they are linked. One knows the type, the other one you may not know. But on the other hand, with the bridge, you will be able to propagate. based on the context, based on the bridge. Okay. But how do you build up a bridge? Okay. Because the journalist may write in many different ways. Okay. The bridge is based on multi-view relation phrase clustering. That means you try to say declares, announces, condemns, or something. Likely this part is a person, it's about organization rather than location. Right? So if you got this relation phrase clustering, even they use different verbs, different verb phrases, you'll be able to group them together, say, oh, the left-hand side likely will be the same type. Okay, so that's the power of relation phrase clustering. Okay. So with this, we probably can see this whole class type has three major steps. One is candidate generation. Candidate generation means you use phrase mining, you find this one, you can do the type, you get a good candidates. Okay. So the typing is on those candidates. Okay. Then the second one, like we said, is construction of heterogeneous graphs, like the one we just shown. Okay. The third one is relation phrase clustering. That means we get many different ways to say it, but if they may imply either left part or right part or of the same type, you can cluster them together. Okay. So now we see the first step is candidate generation. Candidate generation for noun phrases essentially just use phrase mining plus generic part of speech tagging. Okay. That means the phrase, if they do not have a good syntactic structure, like food was good, you use part of speech tagging, you find this one actually it's not a one phrase, it's like a sentence. You just remove those phrases which are improper. Okay. Then you get good candidates. This one was originally, when Xiang did it, he was used top mind. Now you definitely you can use sec phrase, because sec phrase give you a little training. They've said food was good is not a good phrase. Then the similar ones also not good phrase. You can take them off. But part of for top mind you will not be able to, because you don't have anybody train you. Okay, this is completely like a clustering basis, unsupervised. So for top mind, you do need more on the part of speech tagging, because otherwise you get a whole sentence, you treat them as a phrase. You will make big mistakes. Okay. So, but even you sec phrase, you add a little part of speech tagging will help you. Okay. So that's the one that's about noun phrases, or you can say entity phrases. Okay. Then for relation phrases, essentially is you get a verb, you try to find the verb, preposition, and the verb may be integrated with preposition, or in the middle they may even have a bunch of other words. For example, like this, cause major damage on. Well, this one, like cause is a verb, and on is a preposition phrase, but in the middle you may have quite a few other things. So they just group this one as a candidate of the relation phrase. Okay. For this first step, because you want to do the candidate generation, what you need is a good recall. That means you grab the good candidates, you say, I'm going to type it, or I'm going to identify this one as a relation phrase, later I'm going to cluster it. Okay. Then you want high recall. And you probably can see using this method comparing with noun phrase chunking. Noun phrase chunking has been used very popularly in natural language processing. This usually is trained. That means you need to give a lot of training set or curation. Okay. You actually can see the recall for the new method, for class type, this new method, recall is very high. For New York Times it's high, for Yelp it's high, for Twits it's also high. Okay, because once you get this high recall, later you still can adjust it. If you make it wrong, You know this one phrase, you say this, instead of relation phrase, you say this is an entity phrase. You may make something wrong, but it doesn't matter, okay? Because later we still have a chance to do a lot of adjustment. So you probably can see, if you look at this example, you can see this EP, this blue one, is an entity phrase. Okay? Some longer, some shorter. For example, this one is pretty long. You can see this is Dallas-Fort Worth International Airport. This pretty long one. It's just one entity phrase you grab. Using phrase mining, you'll be able to recognize it. And some relation one, you probably see this relation one is a reach, forecast, a cost, like at, dropped. Those noun or preposition or their phrases, you grab them. Okay, so that's the first step. Once you grab them, the second step is constructing the heterogeneous graph. Okay. The constructing heterogeneous graph is the same graph I just shown you before. So you probably can see the major thing is based on these candidate entity dimension and based on the entity surface name and the relation phrase, you compose them into 3 different types. And the concrete one, you're going to build links based on the sentence you are analyzing. Okay. Remember, this one was done not for one document, for many documents. Okay. That's a major difference between the typical NLP processing versus this one. Okay. Like I said, the NLP processing in many cases just analyze one sentence, one paragraph, or one document. This one actually get hundreds or even thousands of documents you put together to build a one graph. Why? Because you want to cross the documents, you want to do some kind of clustering, some kind of propagation. For example, if one document you found announces, the other one find declares, and finally you find based on the existing thing, you actually know they can be clustered like one. So across the document, you may help each other. Okay. Then a very important thing is disambiguation. Okay. That means once you try to propagate, okay, you're not looking for one case, you're looking for many other cases, and you're looking for the context as well. Okay. So you build a subgraph, you actually may try to help you to do propagation. Just to give you a simple example. Okay. The previous many cases, like Washington, typical example. Then you can go to your general dictionary, you can look at the distribution. If you go to the general wiki or dictionary or corpus, you find Washington likely will be a state. The state chance is very high. Okay. Then, in many cases, like here, you see as concerns whether Kabul is an ally of Washington. Okay. If you do not know, you just blindly say Washington because the chance to be state is much higher, you will mark this Washington as a state. But obviously, it's wrong, right? The Kabul is an ally of Washington by human. You can easily say this is not a state, this is the government. Okay. So, but if you find it's ally of on the right-hand side, this one, likely the ally cannot be state, likely could be an organization or a government. Okay. So in that case, you can see the chance to be government will become very high. Okay. So you probably see these 2 distributions will be very different. Which one will dominant? Okay. Usually you probably see you get a local context. Okay. Like this relation phrase, this local context actually may override your general distribution. Okay. So that case, this local context said this likely to be a government, you likely will give more weights on this government. Okay. So that's the general philosophy, how you try to disambiguate those, like ambiguity, you get into different types. Like this one, you have 3 or 4 different things. You need to make a decision. Okay. And how do you really get this is ally of? You can say, oh, this one, because nobody train you, say it's ally of, at the right-hand side likely will be a government or an organization rather than a location. How do you get that? Okay. You get that still from phrase. Okay. How? Phrase did not give you concrete one, say it's ally of. That's exactly the power of relation phrase clustering. That means you have many such cases. Some you clearly know the distribution. Okay. You probably can see here. Just give you a simple example of how you can get this. Of course, we are not using its ally of, but we are using like this. You probably see this graph. This graph is different color. This purple one means this is right argument. This red one means left argument. Okay. So you probably see here you see the different statements, different comments. They start propagating, along this big graph, in an iterative way. You probably can see something you know, something you do not know. For example, here you say serve up cheesesteak sandwich, and here's a beer, here's a wine, here's a pizza. Originally, you may not know what should be the type, but something could be labeled. Okay, for example, you go down to Wiki or go down to Freebase, you may find a beer actually is a drink or is a food. Okay, then you find this cheesesteak sandwich is food. You may know this, okay, but you may not know the others. Typically, maybe you say beers, wines, pizza, I know it, but the other things I do not know how I can use it to propagate. Okay. The propagate actually you can see is beers and pizza. They say serve up beers or serve up pizza. Okay. Then you will know these serves at the right argument likely could be food. Okay. And the food the chance is high. Then suppose you do not know this cheesesteak sandwich is what. But you have served up for others, you know it, you will say, oh, this steak sandwich likely will be food. Okay. Then you see they also link here is they provide a decent selection of. Then these provide decent selection could also be food. You can see. Then these two things may be clustered, may be grouped together. Say this one actually is a cluster. Okay. The similar thing here you probably can see. If you do not know this moussaka is what, but you see the pizza, they say the pizza is very average. Okay. Then this moussaka, they say is very average, likely is also food. So you probably can see you use this either on the right-hand side you can make a cluster, or on the left-hand side you can make a cluster. This relation phrase clustering can help you resolve some unknown types. Right? If you do not know, you make a cluster, then you propagate to those things you do not know. Okay. Remember, all these propagation are statistic-based. That means my propagation and your propagation, even with conflicting, we do not erase each other. Everybody get your statistics. It's more like a presidential candidate. Okay. You vote this, he vote this. You finally get a statistics rather than say my vote overrides your vote. We're just competing, right? So to that extent, this is the same game. Okay. Now you probably can see how we should do this. Is you make mention, you make this correlation, you build up this graph using, you can see here, there's some subtlety. Here you probably also can see White House. Okay. White House actually is also ambiguous because White House could be a real house, could be a location, right? But White House also may represent U.S. government, administration part at least. So then you probably see here they said, sad to think the White House fell. It's hard to release Obama's birth certificate or something like this. Okay. Then here, by a human reading, this White House is not a house. It's not a location. But, because the White House felt it's hard to release Obama's certificate, birth certificate. This must be a government. Okay, so organization here. So you probably can see, but here you can, another one is the ceremony is located in White House Rose Garden to honor now. Okay, that White House and Rose Garden get together. This must be a house, must be a location, right? So all these is based on what? Based on the context. To some extent, it's based on the relation phrase. You can see it's located in White House. This White House must be a location, right? And you see Rose Garden, you see all these. It's clearly it's a location. But the other one said a White House announces something. Oh, it is an organization. So you probably see for all these, you are looking at the context. Context means you look at the relation phrases. You even can look at the nearby entity phrases, like a Rose Garden actually may affect you to say White House location is bigger. Okay. So that means what you do is you want to use mention correlation. Mention correlation means you get Rose Garden correlated with White House. That the White House is location is bigger. Okay. You say located in is bigger, right? So you probably can see there are several key things you can handle. Okay. Then the key is, in many cases, people write it in very different ways. Okay. And you can recognize in this way, but once they write in a slightly different way using different phrases, you may get confused, okay, or you may not be able to propagate. In that sense, to take care of this sparsity, you need to do cluster. That's why relation phrase clustering become pretty powerful, because you can cluster them, and some bridge originally you cannot build. Now you say, oh, all these are similar bridges. They have the same kind of type at the right-hand side. Then you just cluster them together. The bridge is open. Okay. So that's a general idea. And what are the bridges? Okay, you can see two relation phrases tend to have similar cluster membership if they have similar strings, context words, left and right argument type indicators. You can see how do you propagate? You use multiple signals. Okay. One, we already said you have a left and right hand argument. You say, oh, they have the same, they must be the same. Another one is context words, like Rose Garden. Okay. And similar strings, also you can do the propagation. Then you see, if you can use more signals, and you are confident with those signals, the clustering becomes pretty powerful. Right? Then you probably see, if you look at why we want to do relation phrase clustering, you probably see the general statistics. You see there's 37% relation phrases has less than 3 unique entity surface names. That simply says, if you really look at the same relation phrase, you look at the entity, they are all different. They are very different. You only have less than 3 unique entity names. And it's hard to model the type signature because they are very sparse. You want to do clustering. The clustering, actually the important thing is soft clustering. That means when you do the cluster, you just give them a probability. You say this probability is higher to get together, right? Because there are so many cases, you still distribute them. You can say nothing very firm, but finally the higher distribution, higher probability will win. Okay. And this is a phrase frequent relation phrases. You get the count. Then you look at the infrequent ones. You want to get, if they share similar cluster membership, these infrequent ones will get help. Okay, because you get a frequent one, you propagate down to infrequent one if they are in the same cluster. Okay. So a lot of things you can use, just the left and right arguments, those type signatures, you can use them. Okay. And also you can use relation phrase similarity. That means that they have the similar things, you can group them together. That's based on those we just said, a string, context words, left-hand, right-hand argument. Then finally, you put all these things in one equation, which is optimization. Essentially, it's joint optimization framework. Okay. The joint optimization framework means you have an objective function. Okay. For this function, you get three major components. They mutually enhance each other. Okay. One component actually was evaluated based on the type of propagation between the entity surface name and the relation phrases. That simply says this one is based on something is labeled, something is not, and they share the similar things. You try to do the type propagation. Okay. Another one, the second one, is based on multi-view relation phrase clustering. It simply says you really want to group those relation phrases if they imply the same left argument or they imply the same type for the right argument. That means, for example, you say located in. Likely on the right argument is a location. Okay, so that's clear. But that means you can use the clustering. The other one may say situated or something. You do not know situated, but you find in many cases they are in the same cluster and located in or situated, in. It will be the same thing. So this is multi-view relation phrase clustering. And another one is based on the mention correlation, based on mention modeling. Essentially, as you look at the context, you actually can help. So these three things put together, I do not say you have to understand these formulas, but you probably can see, actually the whole thing is open source. One you can download, you can read it, and you can use it. And these three things getting together, the joint optimization, joint optimization framework means those three things getting together, you try to minimize the discrepancies, or you can maximize the one who can give you the best argument. So essentially, this joint optimization says you just turn them into a loop. They finally, you can get more clusters. You will be able to bring other things into more like better correlations. And the better correlation, you go back, you can make the cluster also tighter or more confident. Okay. So with this loop, finally it becomes stable. The propagation will help each other finally get a much better result. Okay. So that's the role of the joint optimization framework. Then the whole thing actually is more like an EM algorithm. You put this function there, you turn them into a loop. Okay. Why you turn them into a loop? Because some they can bring the closer one, tighter, you get a confidence. Then the other far away one with something in common, they will gradually bring closer and closer as well. So, you get more things resolved, it helps build more bridges. Right? You build more bridges, you get better clusters. So that's why you think this whole thing, the cluster type algorithm, is an iterative algorithm. Okay. So that's another view. You probably see the top of the trees. This is really big. Right? Then we look at the experiments. Okay. This experiment actually is somewhat convincing because I actually last year I give a keynote at the ACL 2016 conference. ACL is a top computational linguistic conference. Those are all the natural language processing people. They have been working on this for many years. And we have to compare with most influential algorithms they developed. Okay. So the first interesting thing is we use pretty sizable corpus. It means that we told them if you analyze one document, we definitely will be beaten badly by NLP people because they have so many tricks to analyze only a single document. But we actually use lots of documents. They help each other. Here you can see we took 2013 New York Times, which has 110,000 documents. The major type are the event, person, location, organization. Okay. Then we also use Yelp reviews, which have 230,000 documents. The major type of food, job or hotels or something like this, right? Then 2011 tweets, we got 300,000, and the major type are event, product, person, location, those things, right? But remember, tweets is probably the most difficult one because tweets is very short, and they write in a very brave way. They invent many, abbreviations. They put it there, and also they do not follow strict grammars. Okay, so that's why the tweets for everybody is a big challenge. Then we check the freebase. The freebase actually, we try to see the seed mention set. It means something can really serve as a seed we can use to propagate the others. But unfortunately, the extracted mention only less than 7% are the linkable seeds. Okay, that simply says you got these seeds you can link to the document, to the corpus. Only 7% can be linked. The 93% you have to work out by yourself. Especially many things in Yelp and the tweets, they are poorly linkable. Okay. Then, how do we evaluate this? That means you said it's right. How could you prove? Essentially, is we got this corpora, we got the target type. Okay. We manually annotate mentions of these target types. That means we took those documents. We manually say this is what type. Like you say, White House is a location, or White House is organization. You manually locate to do this, but you don't put this one into your program. Okay. When the program got this, program has no annotation, no judge. Okay. But you got the results. You manually label this. You get the program. See how the machine give you the label. Then you check with human label to see which one the machine, you assume the human label is right. Okay. Of course, you may say the human may disagree. Okay, that's possible. But we basically getting those documents are not quite disputable. Okay, like in this case, White House is organization. This case, White House is a location. Everybody agrees. Okay, so then you ask machine do it. You check the machine output with the human label to see what's the accuracy. What's the coverage? So that's why we use F1. F1 means precision and recall. You want to get a high recall. You also want to get high precision. Okay. So that's the evaluation. Evaluation metrics, essentially we just use the typical one. Precision and recall, or their harmonic mean is F1. So you basically use F1, probably the best measure for everybody. Okay. Then we have to compare with many established methods that people are using. Okay. So the typical one, we actually listed the most influential ones, almost all those influential ones. One is Stanford pattern-based learning for pattern. The Stanford one, if you learn the course in Coursera, you probably saw Stanford has quite a few quite known professors. One is, I think, is Manning, Chris Manning. He was a professor in Australia, but later joined Stanford. He wrote statistics, natural language processing or something. That's a very thick, very nice book. And he also wrote a book for information retrieval. I think there's one very popular information retrieval book written by him. He's the president of ACL. Okay. And they have quite a few other professors. They got a method. Another Sam Pegger, another is Feiger. Feiger actually was done also very famous one by University of Washington, a group of machine learning and natural language processing professors. Okay, so this Feiger is a very influential one. This is NLP-LB and Apollo. There are quite a few ones. We mainly compare these several most influential ones. Okay. Then for us, we actually got, we have several, the one we call class type is the one with all the three things combined together. We remember we have three major parts. One is on is a clustering or no clustering. That means we use clustering, but we take, there are three optimization methods. We take each one off. We just check whether we can miss any major components, what it will be performed. You probably can see all the three components, dimension propagation and like the type propagation and no clustering and all these things. Actually, like this one is you perform hard clustering, then do type propagation, but the other one we do is soft clustering, right? So we take these, change everything one component at a time and to do the testing. Now you see the results. This table, of course, to get this table, you have to do lots of experiments. And the interesting thing is we use these three big corpus, New York Times, Yelp, and Twit. Okay. For these three, if you don't want to see precision recall, just look at the last column, which is F1, because F1 is a harmonic mean of precision recall. So probably you can see, like some, for example, Figer actually on New York Times is very good. They got a 0.88. That means among these several methods, Figer actually got the best. Okay. But if you look at this, you can see we got a 9394. Okay, it's substantially higher than Figer. Even we knock down, like even we do not do relation phrase clustering. Okay, we actually still a little higher than Figer, but if this one is worth mentioning. This is the two steps. You probably can see. Overall, you take all the components, put them together, you get a pretty high. Okay. Then you look at Yelp. Yelp actually is this NMPRB. Okay, got the highest among those existing methods, and you probably see this one actually we got 0.8. That's comparing to the others, 0.5. You get it pretty high. When you look at Twits. Twits, of course, is difficult to everybody. Okay, but you probably see here, Figer probably still the best. It got a 0.3, and this one got 0.45. Okay. Of course, that implies Twits will still need to do a lot of work because 0.4 or something is still pretty low. Okay, for the real use in a fully automated way, it's still pretty low. Okay, there are lots of work to be done along this line. But you probably see if you can get this kind of F1, like for New York Times and Yelp, you can get this kind of F1. In general, you can automate the process. That means without much human intervention, you basically get things right. Okay. Then you can do something quite real. Of course, there's this one, I probably should disclaim is this. This is only for the major types. For example, if you say Donald Trump is a person, you can recognize Donald Trump is a person, Ted Cruz is a person. But what kind of person, actually for this method, you did not get it. That means whether this person is a politician or Donald Trump is a business person, at what condition? Or even in reality TV or something, he could be an actor. Okay, so at a different condition, he could be different thing. Okay, so that one needs further study. Okay, needs refined typing. But the refined typing, the major difficulty is the label itself is not clean, because you go to Freebase. Freebase can give you all the different types. Okay, like Donald Trump. Could be a presidential candidate, could be a politician, could be a business person, could even be an actor at some condition. Okay, so if the label is not clean, you propagate the label, unlikely will be very clean. So that's another line of work to make it right. Actually, Xiang and with some students, even in this class, they work together, work out a new research paper on this refined typing, how to resolve this ambiguity. He just submitted to KDD this year's KDD conference. But since it's not accepted or published yet, we will not address in detail. But you probably see there's still a long way to go to make everything perfect. Okay. But there are some interesting things you can see. Something is easier, something is hard. Okay. You just look at this Yerp and Twits, because these are the most challenging one. The New York Times is somewhat easier. Okay. You probably can see just on different one, like this one is the class type, the purple one is class type, the blue one is class type minus this clustering. There's no class. This is Sam Tagger, this is NPRB. Then you look at for Yerp, you probably can see the food is easier. The location is the next one. The organization is a little harder. You can see even for different types, some type is easier to recognize to make it right. Like a location, you can make it almost close to 0.9. Okay. That means you can correctly recognize the location chances higher for everybody. Okay, you can see. But organization sometimes become more difficult because it's somewhat ambiguous or something. But then you look at Twits. Twits, you perceive everybody drops down. Okay. But for person in Twits is somewhat easier. The product is more difficult. The product, because sometimes you get confused with whether it's a person or something. You may not recognize the product correctly. So these are the things you probably can see. Of course, there are still more things you can work out to refine it. The interesting thing, we try to compete with Stanford NER. They do the training. That means they really ask human to do the labeling. Okay. And after that, they use name entity recognition. They try to recognize the names. Okay. How they do it is like what we said. You get 2013 New York Times. You pick up, of course, carefully pick up 500 documents in a reasonably good coverage, not too skewed to just one thing. Okay. You pick up 500 documents, you ask human experts to label every type in these 500 documents. Then you take this as a training set, then you do the remaining testing. Okay. Then you probably see Stanford NER for New York Times, they do this way. They got this F1, but the class type aggregate far higher. Okay. And Yerp got this, and the class type got this, and the Twits got 0.43, and this, of course, the gap is much smaller because Twits really need human help. They have the human to label the Twits. They can do something better. Okay. We have no human to label the Twits, only based on the free base. You actually just slightly better than the human labor one. But even this one, you probably see, is pretty convincing. Actually, when we give this talk at ACR, Chris Manning was sitting there. Actually, after this, he actually talked to one of my collaborators, Professor Heng Ji. He actually asked her, what happened? We actually work on this for so many years, why this data miner can beat us. And I actually explained to the whole audience, the trick is we use a massive corpus. We do not analyze one document. If you just give me one document, I'm almost dead, right? But you get lots of documents, we build bridges. Okay. So that's a major difference. But anyway, it's a very interesting study, even the first one. Sometimes, you probably saw Google has some study previously said big data really counts. How the big data counts? They say you can do substantial training using a lot of very dedicated methods. But if I have almost whole world data like in Google scale, they actually using this massive data to do some statistics, simple statistics. They actually can beat, for the accuracy, they can beat some very dedicated machine learning method. The major thing is the big data they have the correlation, they have the statistics. And finally, you have the power. Okay. So, but in the real life, you do have lots of things, right? You get New York Times. Why you don't use other documents to help your analysis? And you probably can see here is you can get, of course, this is the real one, like how do you label this barbecue, Phoenix, and the pulled pork sandwich. But if you look at this, probably it's very convincing. This is the example, just a small example to show how it works. You can see the relation phrase, the cluster finally got, could be like, just to give you the first example. You see, this is one is a recruited by, employed by, wanted hired by. Okay. And finally, they put in the same cluster, simply said their right argument or employers or person or organization. This actually is clear. So the simply says, actually, when I give this example at the keynote speech, somebody actually, the NLP people raised their hand, immediately said, if you look at this example, okay, recruited by, employed by, wanted hired by, they mean different things, okay? Because wanted hired by means you haven't hired him yet, okay? Employed by is definitely already there, already in the company, okay? So they are different. Why you put them into the same cluster? Okay. Of course, semantically they are different. We can understand this. But the key is we are not really looking for semantic similarity. We're looking for the right argument whether they are the same type. If they are the same type, this is our employer or the company or organization. So we can put them in the same cluster in the sense right argument means the same thing. Okay. So that's the argument. It's not like we really can recognize the subtle difference of the natural language semantics. We cannot. We only do the clustering. But that's enough for our typing, because we're doing typing, we're not trying to understand what's exactly going on, right? So that's a similar thing if we can see. The interesting thing is here, wanted hired by you in our corpus, we only find 264 cases. These small number of cases, unlikely you make the type very accurate, because the propagation may fail. But if you put the same cluster, this have 5,000 cases. This one has 3,000 cases. These so many cases, you will be able to build a bridge in a solid, confident way. That's why you put them same cluster, they help each other. Right? So that's the philosophy. Okay. That means we can boost the sparse relation phrases with this type information because, there are some others not sparse, not as sparse. Okay. So you probably can see the sparsity, that based on the context sparsity, you can see you get a different F1 based on surface name popularity. You get different F1. Simply says you actually the class type overall you can take advantage of the sparsity one. But like this Figer, which is a University of Washington one, once they get a very sparse one, they actually tend to get a very low F1. If you can see, once you get a sparsity, you actually cannot help much. But with type, with clustering, you really can help each other. Okay. So that's the work. Okay, that just published last year. You probably can see lots of people got pretty shocked with this result because this result shows a lot of previous methods. They are very influential one, or some are very popular used one. Actually, if you use massive documents, big corpora, you use this class type, this method, you actually can do better or far better work. So it's pretty interesting in the sense that the people actually look at this thinking, we have to think it differently, do it differently. And that's the power of big data, right? Some people say, what's the difference between big data and small data? Okay, sometimes the big data do help if you use it correctly. So I think there are still lots of ongoing work. Actually, even last year, the paper was not accepted yet. In this class, there are actually two groups of students who are working on, because Sharon was, one, he gave a few, projects to the class. Several groups actually working on with him on the further extension. Actually, one actually just got a new submission to this KDD conference. Okay. So I list quite a bunch of the papers. The one which is said is 2015. Let me see. Yeah, this is 2015 one. There's several ones you probably want to pay attention. Okay, I think that's it. This is another view of this huge, fall. You probably see the fall is really big. They along all the places. This is just one angle. This is the other angle. This is really, really big one. Okay, so now we finish this part one. Okay, then part one basically give you the phrase mining and typing. Okay, so this actually is very important if we want to do text mining. You need to get good phrases. You need to get good types. Then you can build networks. You can do a lot of very powerful things. Okay. Then we get into part two. Part two, actually, in the weekend, there was one student said part two was not available because I work it out. In the weekend, I try to upload to this website. Just somehow, because I have lots of papers there, including our whole group's publication there, they only allow 1 gigabyte. Actually, I got more than 10 gigabytes. Definitely could not remove them because most of them are research papers. So they were forbidden me to upload any new files. So I tried. I finished this one. I tried to upload it. They just bombed me up. So I actually sent emails in the weekend, but they were not checking emails. But on Monday morning, they immediately made it available. I can upload the slides. So I should apologize for anybody in the weekend. They want to look at this part two. They could not find it. So the part two actually is, because this is all text mining, I actually still use the same scenery. But the interesting thing is, you look at this part. These are all people crowded and taking pictures. Very small. You can see those are all the small people taking pictures. And the fort is so huge. You can see that this is the one part of the fort. They have a multi-layers. And these people look really, very small. So then you can see the scale, right? Once you see the people, you probably know the scale. And for this one, I'm going to introduce you some newer method, which for text mining is also very powerful. Actually, two of these methods are not our own group, okay? But it's a very interesting one. So both of them was just published in 2015. And the last one actually from our own group, Jialu Liu. And the paper is not published yet, but it got accepted by WWW 2016. Okay, so but I think it's very interesting. That's why all three papers are very recent papers. I just put them as a part two. Okay. Originally, I do have another paper, but the paper has not been accepted yet. I just took it off. Okay, until it's accepted, I will put it in. Okay. So. These two papers essentially is done by Microsoft Research, but one of the second author actually now become a student in our class. Okay, so actually it's also, for any explanation, my explanation not accurate, you can ask the student because he can give you much better, insight on their work. So the interesting thing is still on information networks. Okay, if you look at the paper title actually is a line. It's a large-scale information network embedding. Okay. So the general idea is, if we got an information network, especially the heterogeneous information networks, it becomes very, very powerful. We can do node classification. We can do link prediction. We can do visualization. That's one we already shown you. Okay, the network is very powerful. But the problem is they are, for every vertex, okay, you carry the information. The information actually is, you may have many high dimension things. They are in the network. You try to use the context of the information to help each other. Okay. But on the other hand, many context information may not be available. Okay. Just give you a simple example. If you take like a database conference, we often use there's one conference called Sigma, the other conference called VRDB. Okay. These are all on the very large databases. If you are not in the domain and look at these two abbreviations, it doesn't make any sense. You can link them together. Right? So that means the context may not be always available, but you can get it from network structures because they share many similar things. You can, based on network structure, you can put them together. Okay. But the problem is how we can put them together. Then this paper, actually, I said this second author actually now is in the class. Okay. And this one were done by Microsoft Research Asia. Okay. And he was a student in the university. Actually, they worked together. I think this Xiaotu may actually graduate from UIUC in Professor Zhai's group, but he is now a professor in University of Michigan and Ann Arbor. Okay. So he probably went back with them to work together. That's why it's one of the authors. This line paper, the interesting thing is you want to do embedding. Simply, so-called embedding is you want to put some, you want to change this every vertex into some kind of vector. Okay. It could be a little high dimension vector, but these vectors contain lots of information, embedded information of the whole network somehow. You want to put it there. Okay. Then you can embed in different ways. One is you based on first order similarity. Another is you based on second order similarity. Okay. The first order similarity means you really look at, suppose this node 6 and node 7, you mention many times together. Okay. They closely link together. You actually may put a link there. Just to give you a simple example. Suppose you say this one is a Sigma, this one is VRDP. Suppose you look at citation. There are many, many papers cited, both of them. Okay, cited paper in both these two venues. You probably can say if these links are so tight, they're very heavyweight, these two are similar. Okay. The similar thing in Facebook. If you see these two nodes, it means two people. Okay. If they have a very frequent communication or they have many, many common links or something, you just think these two linked so close together, you will say these two are somewhat similar. We can put them in the same cluster, right? That's the first order. That means nodes with strong ties tend to be similar. You put a node 6 and 7 together. Another way to put together could be this node 5 and node 6. Okay. You look at these two nodes. They may not even have a single link them two together. But they may have many common neighbors. That means if you link to many common things, like these 5 link to 1, 2, 3, 4, the 6 also link to 1, 2, 3, then likely these 5 and 6 could be somehow very similar. You judge the similarity based on their common neighbors. Okay. So you can say direct link, the 6 and 7, is the first order. They call this one the first order similarity. But they share many common neighbors. You can think is second order similarity. Okay. The interesting thing is once you have a network, you can immediately kick in the second order similarity because you can watch the network topology, watch their linking to the neighbors. You make a better use of this. Right? Those are the things you can get. Okay. Then, here we get a little math formula, but I just want to explain this. Okay. How do you calculate the first order similarity? That means you just say these are very tightly linked nodes. How do you calculate this? Okay. To calculate this, of course, you say nodes connected with larger weights. Okay. Larger weights means if you have many, just think about this, if these two people have many collaborate papers, okay, so that means you think they publish paper journal once, you give weight 1. You publish 10 times, it's a larger weight. You pull them together tightly. So that's a larger weight. Okay. That means you can embed your vector in that way. Okay. And how do you embed them? In the very beginning, you may say, if you got this Vi and Vj, these two vertices, okay, these two vertices, you can think about you have a similarity matrix. Here you can say co-author matrix. Okay, you can get a matrix like this. This matrix is, you can think everyone you have a collaboration, you have a vector. Okay, the vector you can think is everyone is a low dimension vector represented by the vertex v sub I. Okay, but you have so many authors, you get a whole matrix. Okay, if you want to see these two how they do the collaboration, what you need is you take this one's transpose, you multiply, the other one. You say the I, this is the vertex I, you get a vector. This is vertex J, you get a vector. If you want to multiply these two, you actually have to take a transpose of one, you time the other one. This is dot product, right? So and this is like a sigmoid function. Basically, is this exponential e to the power of this one, right? So, but anyway, the general philosophy is, if you get a tighter, more common, things you can put together like a common papers, okay, then your similarity will be higher. Okay. Then what you need is a normalization. Is you have to look at all the other vertices, then you do the relatively, whether they are tight or not. So that's the reason you watch their John probability. Then this one is this is the empirical John probability. Basically, you look at the real data. What is the concrete one? This, you get two probability. Then, what do you want to see whether they are very tight or not? You based on a method called KL divergence. Okay, this is a measure. I do not know how many people know KL divergence. How many people know? You raise your hand. How many people know KL divergence? Okay, we do not have that many people know. That's exactly. I put one slide to explain it. Otherwise, you may get confused. This is one slide. Actually, this is the slide I took from my previous CS412, the Introduction to Data Mining course. I took this slides as a very brief introduction of the KL divergence. KL divergence mainly is used to compare two probability distributions. Okay, that means you're just thinking about it. You get we still use the previous class type. You probably can see. You have a distribution. Suppose you get a Washington, you get a distribution. There's a government, there's a location, there's a sport team, there's a person, there's a street name or something. You get a probability distribution. Okay. If you think about these two things are very similar, is they have the probability distribution very similar, right? You may get another one, say Kabul. Maybe the Kabul also have the government or a location or something. You actually can finally say, oh, there's a similarity between Washington and Kabul because they have a similar probability distribution. Okay. But Washington may not be similar to, say, to Trump because Trump has no such distribution. Right? So that's the case. You can look at you want to judge it similar or not, you based on their probability distribution. So how do you judge them? Okay. This KR means that these two authors. Okay. Kullback and Leibler, these are two mathematicians. They work out this divergence. They try to compare these two things. Okay, that means you got two probability distribution on the same variable x. You want to see how different it is. One is p, one is q. Okay. You want to see these p and q, how far away they are. Okay. That means whether they share the same probability distribution or they have a very different distribution. Okay. Then how do you check them? This is a formula. Okay. The formula basically says P has a probability, and X has a probability on the this P of X is a one probability, this is another probability. Their difference, you take a log, then you look at their, you get a P, this is X, P of X is one probability, okay, times their log difference. Okay, you actually can say this is log of px minus log of qx. Okay, that's the same thing, right? So essentially, you probably can see this is not symmetric because you look at a q, you change this q to p, the formula derived the value will be different. So it's not a symmetric measure. It's not like you say Washington D.C. and say New York. What's the distance? The distance is symmetric because no matter for the D.C. or the Washington, you turn it back, it's the same distance. But this measure is different. Okay. This one is a measure expected number of extra bits required to code the sample. Okay. That means you get one distribution, you get another distribution, you want to see how different it is. You can use this measure. If this one is a continuous function, okay, some probability distribution is really a continuous function, you just use integral. You get all these, you integrate them together, you get this KR divergence. Okay. So, but whatever, if you do not fully understand it, of course you can read some articles or on the web. You go to Wiki, actually they have much more things you can read. But you just understand, the KR divergence is used to compare two probability distributions. That's it. Okay. Then we go back. Okay. That means if you want to see these two objects, whether they are similar, okay, what you need to see is whether their KR divergence, okay, essentially, that means whether they are very close, their KR divergence is very small or they are very big. Okay, so you based on this to judge whether they are similar or not. So that's the computation of the first order similarity. That means if you think they are very tight, you compare with their neighbor with others. You take this one node, you compare neighbor with all the others. If they are very tight, their divergence will be smaller comparing to the other one. Okay. So then for the second order, we will discuss in the next lecture. But I would suggest, okay, you may like to read these papers because otherwise I lecture it, you may not really understand what's going on, or at least you may not be able to use it nicely. Okay. The paper actually is all in I better show you where you can download the paper. You can go down to this one. You see at the very beginning, I have course-related research papers and other resources. You click this button. Okay. You click this button, you see there are different chapters. And for text mining, you see every one. You can click a button, download it. Now we have lecture this line. You click a button, this is the paper. Okay. Then you can print the paper. You better read it beforehand. That's far better rather than I just spend 20, 30 minutes lecture it. You may not understand it. Okay. Thank you. If you have more questions about midterm, you come to my office. Okay. Thank you.